Good evening, everyone. In today's presentation, I will discuss some of my preliminary findings on the tsunami damage to coastal structures. This project is in partnership with Natural Hazard Research Platform and supervised by Professor Bruce Melville and Associate Professor S.S. Shamsuddin. Tsunami is a Japanese word consisting of two terms. Tsu means harbor and nami implies wave. Therefore, it can be translated as the harbor wave. These two figures illustrates the historical understandings of Japanese and Maoris from tsunami, which goes back to 19th century. These two figures shows that tsunami is not a new phenomena, but after the 2004 Indian Ocean tsunami, it became the interest of coastal engineers, and recently the 2011 Japan tsunami highlighted the need for tsunami research. Here is Ring of Fire, where about 80% of tsunamis occur, and New Zealand as a part of this region is vulnerable to tsunami events due to its long coastline. In this map, I will show you the expected wave heights from local and distant tsunami that can affect the New Zealand coasts, and Gisborne is the most risky part of the country. Just to give you an example of this is Gisborne Harbor, which is flooded by 1960 Chile tsunami, and also Napier affected by about 4.5 meters tsunami. And this is a tsunami wave which is approaching the Littleton Harbor after 2010 Chile tsunami, and also recently because of the Japan tsunami, you can see the water level raised in, the name is very difficult, Tutukaka, for about 1 meter. So tsunami can cause much destruction, as illustrated in this graph. You can see the Indian Ocean tsunami caused deaths of over 250,000 people, and this is considered as the deadliest natural disaster of the 21st century. Similarly, tsunami has high cost. The high cost is associated with tsunami damage, and here again, the Japan tsunami caused more than $200 billion damage cost. So it shows that there is a vital need to have a tsunami-ready community with developing the mitigation strategies and also with improving the public awareness. So we need to know more about tsunami. First, we need to know what causes tsunami. Tsunami can be triggered by the impulsive displacement of large volume of water due to the underwater landslides, earthquake, volcanic eruptions, or meteor impact. And because of some technical problem, we need to run it manually. Tsunamis are a series of long waves, travel the length of the ocean with the velocity of 600 to 900 kilometers per hour, as fast as a jet can fly, and then they get high as they reach shoreline. So they gain the maximum height near the shorelines and eventually breaks and become a tsunami bore. This tsunami bore rushes inland and damages some initial coastal infrastructure and pick up them as debris, and then they carry these pieces of debris, then hit them to the following structures and damage them. And sometimes you can see that the the whole building is detached from the ground and becomes the floating debris. So the research objectives are to find and quantify the force that applies to the front face of the structure. And this has received very limited attention. And then, a scale-up of this result to the full structural scale to be used for design purpose. In this photo, this is one of the few structures that survived the recent Japanese tsunami. The question is why and how. So we need to study more to understand the design characteristics of such buildings. This research will generate valuable data for design purpose, and also will lead to improved resilience of coastal infrastructures to tsunami forces and enhance recovery policies and programming after disaster. For this purpose, a A physical model is developed in hydraulic engineering lab at the University of Auckland, which is consisting of a large reservoir with an attached large wave flume. At the end of the wave flume, an automatic gate is designed and installed to generate the tsunami bore. The gate system allows to rapidly raising the sliding gate together with sudden opening of the shutters. And a scale of 1/17, a scale model of a structure is constructed and situated 10 meters after the flume inlet. And the cross-section of this structure is 300 into 300 millimeter, and it is constructed without openings, just to represent the worst scenario. To give an example of the collected data, multiple tsunami bore depths were measured with depth transducers, and this graph shows you the bore propagation along the length of the channel for different experimental runs. Then we measured the bore height and velocities in front of the structure, which is 100 millimeters and 2.5 meters per second respectively. Then we assume that this bore height is equivalent to height of one-story building. It means that the tsunami can cover one-story building, which is 2.5 meters. And it gave us the geometrical similarity to scale up these results to the real case. So which resulted in 1.7 meter bore height and 10.2 meters per second velocity. Then we compared these measurements with the real case. In the case of Indian Ocean tsunami, the bore height was 2 to 5 meters, and for Japan tsunami it was varied between 2 to 7 meters, while most of the structures they experienced 2 to 3 meters. And also the velocity ranged 4 to 8 meters per second for the case of Indian Ocean tsunami, and 6 to 9 meters per second in the case of Japan tsunami. Can you please run this video? This is a typical experimental run during my experiments, and as you can see, a tsunami bore generated is just rushing toward the structure and hit the structure, and exactly this is the time we measure the force and pressure which applies to the front face of the structure. This video captured with high-speed camera with 210 frames per second. So sorry. There should be a graph. There is? Yes. Okay. So, I don't know, just again for technical purpose and reason we missed this graph. We measured the maximum force equal to 41.6 Newton, and this one is equivalent to the force of 193 kilonewton, which applies on a geometrically similar prototype building and results in 23 kilopascal pressure on the front face of the building. And then based on these results, we just defined a multiplication to the to the hydrostatic force equal to 2.4, which shows that tsunami force is equivalent to 2.4 times of the hydrostatic force. The term hydrostatic force here refers to the force of stored water behind a dam that can exert to a vertical wall of the dam. So during the test, the generated wave caused a mini tsunami in the lab, and you can see part of the wall of the channel was broken. Fortunately, there was no loss of life, and I'm alive here. So, but we spent around $1,000 in repairing the damaged parts. This is ongoing project, and we already done and finished other experimental configurations like testing on different geometrical shape of the structures at different orientations. And future plan is aimed to develop a new instrument, which we call it a smart debris, to measure the impact force of floating debris on the structure. In conclusion, experimental measurements of the tsunami force applied on the front face of the structure are presented here, which was equivalent to 240% of the hydrostatic force that can be applied on the front face. So at the end, I would like to acknowledge the following organization, and also thank you very much for listening to my presentation.